I don't know if I should start. Can I start? Yeah, cool. Hey, how are you doing? Nice to see. Nice to see you all. It's been great. I've been learning a ton, even though it's just the first day. Um, yeah, I actually don't know much about what I'm doing here, so yeah, that's it. I'm just kidding. I'll just be reading docs and using AI, and basically proving that you can do that as well, and just be here. Just the same thing. Um, but I'll still start with a bit of a presentation of what I've learned and what can you do with Noir, and yeah, how can you learn it in an afternoon, even if you're alone, and kind of stretching the concept of an afternoon anyway. Um, I will. I was saying I see that there's questions, so maybe the best way is if I take questions after I did do this little presentation, and then you can ask questions at any time because this is a long workshop. So you just feel free to interrupt me and say I don't follow. I've been getting this error or anything like that. So if this was a round table, I'll just go around the table to try to help you if you want to follow along. We have enough time for that. So yeah, yeah, you didn't pay to be here, so I'm not gonna give your money back. Sorry. That's first thing. I need to say this for legal reason. I'm kidding. No. But you're gonna learn Noir in 1 minute actually. So it's not. You don't even need an afternoon for this. Yeah, of course. So basically, it's this like you have these two people are like in a it's a grok. This yeah. Hackathon or something, and one of them is like, you know Rust, and the other one says, yeah. Of course, he needs to say that he uses Arch because I mean that's it. You need to say that if you use Arch, and yeah, that's just write Rust, and that's it. That's it. Okay, see you. Thank you. Tomorrow it's a nice day. Okay, no, okay. But if you don't know Rust, which is my case actually, I coded very little in Rust. Then you're like, okay, but again, if you know, it's basically going to be the same thing. You just need to understand the concept of a zero knowledge proof, and then everything else is basically the same syntax. If you don't know Rust, then just stay around. Um, but you're like, it can't really be the same, right? So, well, I'll tell you that indeed it can be the same thing. So first, I'm gonna start by talking about how zkVMs aren't zkVMs. No, I'm kidding. No, I can't do that. No, I'll be triggered. No. But I'm gonna talk about zero knowledge for privacy, which is quite the big deal. Yeah. And now then Noir. Like, why do we keep saying Noir? Like Noir. I mean, there was like 2-3 talks in this event that say Noir. And why is this such a big deal? And then I just easily just achieving global peace in an afternoon, which is also very easy to do. And yeah, that's it. Let's start with zero knowledge for zero knowledgers like me. Yeah. So it's very simple, right? I hope you're ready. Let's just start with the basics. Here's a little equation. Okay. I I hope you're following this, right? It's very simple, right? Okay. We're like, yeah, good. I can get this. So now it's simple, right? Now you just need to observe that this is, I mean, right? Okay. And this is a problem in ZK. It's like every single paper starts with, oh, this is this little equation, and everyone is like, oh, cool, I can understand this, and then immediately goes into PhD level maths, and if you just want to build something, you're gonna have a bad time. And so, why am I doing this to you? And the reason is because I've tasted it. We've tasted this at Aztec since we've been working with ZK for 8 years. So yes, we were there. This slide is old because it's 8 years ago now, and you can actually like you can write your constraint system just using math. Just go write C++ and yeah, do it. But then people started saying, yeah, I mean, it could be a little bit easier. There could be this kind of circuits, so they can understand. So they design zero knowledge programs as kind of what we still call circuits these days. But then they become like this, like it's a huge mess. Programs are enormous because they are basically dealing with stuff at the bit level. And yeah, sometimes you're like, where is my XOR gate in with all of this mess? And and so that's when we started to think about programs, not necessarily circuits. Programs that prove. You have programs that execute. That could be a game, could be an app, could be a website, something like that. Then you have programs that prove things. But for that, we need this nice layer of abstraction, and that's why Noir started. It is still, all the math is still there. It's just you don't see it. So people that are zero knowledgeers like me, they can still do zero knowledge. So why Noir? Yeah, because zero knowledge is cool. You can prove statements, computation. Yeah, just like Savius said just now, you can basically prove the knowledge of a recipe of Coca-Cola, and without revealing what the recipe is, and still say that it's an original Coca-Cola. Stuff like that. That could be interesting for enterprise, even if you're into that. But it's also hard because, yeah, yeah, it's as I said just now, like it very easily goes into PhD level maths that you may not understand or want to. So Kev, which is the original gangster for Noir, was like, yeah, Rust is nice. Like, no, I like Rust. So he copied Rust. He could have done that with any other language. Actually, I think he likes Python, so it could have just done that with Python. Just said Rust is cool. Okay, and that's how Noir was born. It's just a language, right? It's just a copy of Rust. The closest it is to Rust, the better job they're doing. That's basically. After 2 years, more than that, no, it's very good, right? It looks like kind of black magic thing. Now I'll show you. You're gonna be surprised. These days, I can say that the Noir is the de facto zero knowledge domain specific language. I couldn't say that some time ago, but I mean, the moment that Vitalik tweets about Noir is like, okay, that's it. Like my job is done, right? Because it is the de facto language. Everyone is using that. So I'm honest. I wouldn't have said this a year ago. So what do you want when you build something in general? You want something that is fast, that won't take 10 seconds of Twitter scrolling to prove, right? You want something that is powerful, that you couldn't do any other way. Yeah, zero knowledge is basically, there are some problems that can only be solved with zero knowledge. And you also want something that can actually be used. It's not it's not a pain. You don't have to download 400 megs of proving keys on your phone or something to do. No, it just goes and just download an app and it's done. If you use ZK Passport, that's the perfect example of an app that just comes with everything inside. You just use it and go on your way. So some examples of things you can do in Noir. Just a simple guessing game. I think this is the default program that comes. Just this is it. You just define two variables. Define one as public, the other one just by default privacy, because privacy is normal. So that's you get all the inputs are private by default. If they are all private, that wouldn't make much sense, right? But anyway, you need to define which ones are public. And then there's just an assertion that says, yeah, that's what the verifier will prove. Will verify that X is different from Y. I think I can say this is simple, right? Pretty much zero knowledge proof. So proving that you know a password without revealing what is the password. That is really cool example, like for login website, you go log in on a shady website. You don't know what they're going to do with your password, and like you shouldn't, right? You shouldn't. Your password is something that is private, so you can you could be able to prove that you know what the password is without revealing what the password is. So again, another simple circuit. You can import the basic hash function. These days we would actually use Poseidon, not Pedersen. Poseidon is more efficient these days with Protocol Berg. But yeah, the same thing. You have a private input, which would be the thing that you want to keep private, and then a public input, which would be the hash, in uneligible thing that you can ever guess what it is. And then you just have an assertion that proves that um, within the circuit, you're proving to the verifier that you know a password that, when hashed, equals the thing that everyone knows. So if you wanna if you wanna have your own unicorn, this is it. You can copy it, right? You start from here, and then you ask ChatGPT to do the rest. It will build your company for you, the marketing and everything, right? So yeah, if you wanna unicorn, it's an easy way. And then Semaphore, which is I would say one of my favorite projects in Noir, which is proving that you are a member of some group. Actually, for this workshop, I was like, maybe we could use ZK email to prove that you have a ticket to be here, and then we could use it for voting and stuff like that. It was hard because of the ticket came in an attachment, so it was not that easy to parse. But yeah, I would use something like this. Like I would say, yeah, if you have a ticket, you have a nullifier, and then I'll just put nullifier in a huge Merkle tree, and then you would prove that you are a member of this Merkle tree. So you have a valid ticket. You could make a vote, like a voting. You could do some really cool things with people in here. The least of all, having a chat of everyone that is in this event, or people that have a ticket for this event. So yeah, pretty cool. But is it fast? That's what everyone asks, and it triggers me to crazy stuff, because what do you care? Do you care about proving in 200 milliseconds and having to download a 400 megabyte proving key, or do you care about proving things in 1 second and not having to download anything? You tell me, right? So this triggers me beyond you can imagine. I don't care if it's fast. If it works, and other solutions don't, then I would use the one that works, right? So, but still, it depends. Like, it depends on your backend. Like, in the case of Noir, we tend to use Protocol Berg because it's the one that Aztec Labs developed. But you could use others. You could use there's World is building their own Grot16 based backend. There are other teams building, so you could actually change your backend and deal with all the trade-offs that come with them. And then a program, like, yes, it's very easy, it's very simple. You could still improve it, right? You could still say, I mean, you could use constraint functions for not constrain certain computation that you could save and without any security problems. So yeah, you can definitely improve your program and make it be faster. And then finally, what I was saying, it's about your app. Like, what do you care? What do you care? You want something that works or something that doesn't, but it's fast, right? So yeah, actually, nobody cares, and we start to see these like real world apps that are coming in, especially in mobile. They use Noir because they understand that it's the only solution to deliver a product. So yeah, it's the only usable one. Yeah, you can write code, not circuits, because like, yeah, we're talking about the different backend. This is the case of a Grot16 backend. You can just use the same verification key for the same verification key for the same circuit. Different verification keys are kind of small. You can put them on a smart contract. But the CRS, like the universal setup, it's universal for all the circuits. So that's a big thing you want to take into account when you build an app. You don't want to have different circuits for each Merkle tree depth, and then you don't even know which one you have to download. And when you do, it's 200 megs, right? So yeah, the same thing about gas cost. It's like, oh, but it's less expensive to verify some other backends. Yes, it is. Yeah, like from some situations that would be useful. But are you also paying 200,000 gas to verify something on L1? Who will be doing that? Nobody. So that's the thing. You don't care. You care something that works. Care about something that works. And then yeah, mobile. Yeah, mobile is a big one. You want something that works on the phone because that's where most traffic comes from. You want people use their apps to pay for payments on their phone. They use their apps to use social networks on the phone. So you want something that works on the phone, so it's lightweight enough, and you don't have to download a ton of data. You don't you don't take a ton of time. You don't have server-side computation, which is useless. I mean, if it's server-side, then it's not private. So yeah, about achieving global peace in an afternoon. Yeah, just yeah. No, I may have oversold this, so I'm just not do that. Um, so about this, the next part of the workshop where we're gonna actually build something, we're gonna see some Noir tooling, then we're gonna write some Noir code, and then prove something using. We'll try to do it all in the CLI using Remix IDE for to be easy, but maybe we can use AI quite extensively to make things look good, like on a browser or something, like just to have fun because we have some time today. So some links. This is the Noir Discord, which you can join. You can zoom in on phones to read QR codes. That's something I didn't know until yeah. Sorry, I'm dumb. Um, yeah, you can join the Noir Discord. This is the Noirlang, which is basically everything that I'll be doing today is in the Noir docs. So you can say I'm just here reading Noir docs, which is cool. I wrote them as well. So, you can pretty much everything will be from there. And then there's this my link tree, which has two links at the top. One is cheat sheet. So it's just like it has some commands that I'll be running. So if you fail in some process and if you take a little longer doing something, you can still catch up with the workshop because you can run these commands. So I thought that would be easy. And then there's also I call a 40 IQ code space. So if you don't know what code spaces are, they are just basically IDE. It's like an IDE that runs on the browser and on a remote server. So it comes with Noir, with BB, everything you need to use. So if you don't want to install it locally on your machine because you don't care too much, you can use this code space. Cool. I don't see phones in the air, so I think everyone has scanned it. Cool. So first thing, noirlang.org. Okay, you can go here, read the docs, and then second thing, you have an AI that you can ask stuff. Okay, this AI has knowledge on everything that's in the docs, so you can ask questions here. What's not in the docs? I mean, yeah, good luck. But most of it is in the docs. Most of the stuff in the code base is indexed in the docs as well, so should be fine. You have search. You have basically everything that we'll be doing here today. And then, as I said, this cheat sheet with the code space. Cool. So things I won't have to do, but I'll show you, which is the first installation of Noir. So if you know Rust, you probably have used Rust Up, which is the easy way to install Rust. So same thing here. It's like you install Noir up. This is the thing. You install BB up, and then you can run them Noir up, BB up. So in the cheat sheet, you can copy these. I'll do that. Just gonna open my IDE. I'm just gonna run this. Okay, then I'm gonna run the other one. Okay, don't forget this cheat sheet is in my link tree, which is link.tree/ck Pedro. Right, it's here, cheat sheet. So I'm gonna copy the second command to install BB up, and then I can run both. Okay, and this will install Noir up, Noir. It will install Nargo actually, which is the package manager for. It's basically the everything binary for Noir, and then it will install BB. BB stands for Berg, which is the backend that I will choose to use today. Also because I don't know anything about the other ones, but BB is nice. So I can run Noir up here. It will install Nargo into this binary. So this should be in your path already. If it's not, then you just close your terminal, create a new one, and it will be there. You know it's there if you go Nargo version, and you'll see it's gonna be 1.0.beta.6. Okay. Yeah, this is some great naming, almost like OpenAI level. And then BB, you can same thing. You can know BB up. You can run BB up, and this will install whatever version for BB, which is going to be version 84. And then you can know it installed correctly if you go BB version, and it will tell you which version you have. And then, as always, as with good binaries, command line interfaces, you can see what they do if you go just Nargo and don't say anything. It will tell you what can you do with it. And the same for BB. Oh, BB actually needs help. So it will tell everything here. There is no documentation site for Berg, and that's totally my fault because I've been meant to be doing this for some time. But the documentation for BB would always just be the repository at Aztec. So you can go Aztec protocol /Aztec packages, and then you have Berg. So the documentation website will just be this, right? Just in a nicer way. So it has pretty much like everything about BB, including how to build it and stuff like you. If you're a geek, you wanna question. Berg. Yeah, it's the proving backend. So when you use a zero knowledge program, you need to execute the program to generate the inputs. That would be the witness. We call it the witness, and then you would put this put this witness into a proving backend. So that's the actual thing that will prove. So you always need two, not always, but in the case of Noir, you always need two parts: one that executes and one that proves. We call it the front end and the back end. Front end would be Noir, back end would be Berg. In this case, yeah. But again, you could use different proving backends. They all come with their own different trade-offs. Yeah. By the way, we have other questions or not really? No. Yeah, feel free to just raise your hand and yeah, I hope I can see. Yeah. Yeah. As I said, like if you use like a proven backend that uses Grok 16, you definitely get better speeds and less gas on on-chain verification. But then you get one trusted setup for each circuit. So if your circuit happens to be, if you just need one circuit and always gonna need that, then okay. This is actually a very good argument. I don't know if you remember Sismo at the time, but I had an argument with the guy, and he was saying we don't need it. Like our circuit is done. Like we won't ever change it. So why would we change to a different backend? And he was right. There was no reason. But most of the time, you want to keep track of that because maybe you have a bug, you want to fix it, or maybe you don't know which circuit you need to. So really, it comes with the trade-offs on what you're trying to build. So yeah, yeah. Mm-hmm. Okay. Yeah. The question. I'll just repeat the question. The question is why is Brottenberg uses BN254 as the little curve and not BLS 381? I don't know exactly how to answer that question. Um, yeah, I really wouldn't know. Like, uh, yes, that's a good one. But yeah, yeah. I mean, you can still do operations on BLS 381, but they are out of curve, so you need to basically do non-native computation, which is slow. So, but yeah, I think there's a trade-off there with and definitely as you mentioned the compatibility with the EC opcodes in Ethereum would maybe be the biggest reason. I don't know if Savio has more information about that, but I would say that's probably the reason. Yeah, but yeah, good question. I just sorry, I don't know a definite answer. Cool. So yeah, uh, at this point you should have BB. You can go BB/H and see what commands do we have here. So to start, it's gonna go Nargo new. Okay, so if you see Nargo, you can go Nargo new and Nargo init. Um, I'm gonna go Nargo new because it starts in a new directory. So it's a name workshop. Right? New / name. Okay. Oh, okay. Or a workshop. Right, nice. Cool. So I have a new program here, and you can already start with this one. One thing that you will notice, which is really cool, is that you have tests. And also, if you're using your own laptop, you're gonna notice that you have this little very nice um, language server, which will tell you basically it will autocomplete stuff for you. It will, I mean, it's really pretty amazing stuff, and you can just run this test, for example. It will just run one test for you. Um, so you could actually have tests that are supposed to fail. So in this case, this is the default program, as I said, proving that I know a number and that I won't tell you what number is, and yeah, proving that you have failed to guess my number. But I can actually run a test or write a test that is supposed to fail. So I can go like test should fail, and then I can go fn test fail, and then I can do like main 1 1. So and then go to nargo tests. Actually, I need to cd into that folder nargo test, and I see that two tests pass, which is correct. Like this one is supposed to fail. Actually, you can even have assertions that are supposed to fail with not the same, and then tests fail, and then says should fail with. I don't know if the syntax is correct, but yeah, I think you get the idea. You can actually make it fail with a specific reason, which is good test practice. Cool. So like, okay, I showed test. Remove it now. But this is just a test. What can I do if I want to actually build a zero knowledge program with this? First, you need to execute it to get the witness, as I was just saying. To execute it, you just go nargo execute, and it will basically oh, in this case, it needs an prover.toml. So actually, I forgot one. Now go check. Now go check will just read these and see, yeah, what are the inputs you need in your program. So it will auto-generate this prover.toml file. And here's that's where you put your inputs. This, if we are Alice and Bob, and I'm Bob, and I want to prove something, I won't reveal this because that will reveal my private input. So this is I can ignore this. Okay, this is just for proving. So now I can actually go now execute, and it will hopefully work. Yeah. Now you have two files now. There are one of them is just tells you the version and the ABI. So I mean, you probably know what the ABI is because it's widely used in Ethereum, and you also understand why this touches Aztec because it's an ABI. So, and then there's the bytecode. It's the actual thing. It's base 64 encoded actual thing that we are proving, which is actually not very big, as you can see. And then there's the witness, which I don't think you can even open. But that's basically the witness is the solution for your circuit. So it's what it's basically it's the solution for the thing that you want to prove, but not yet proven. So you need to feed the witness into a proof. That's where the backend comes in, and this is all about Noir. Like that's done. Okay, you can uninstall it. No, don't. But yeah, because Nargo definitely has other things. But yeah, this is all about the front end. You now have what you need to feed into the backend. So this is where BB comes in. So a new project, basically the same team. Not the same team, but but yeah, it's a different project. Berg. So Berg, you can do cool things like gates, get the number of gates of your program and know how big it is. So you can go now go BB gates, and this will ask you like some things about the number about your program. In this case, it will ask me for I'm in a workshop, so I want to target workshop JSON. It will tell me how big is my circuit. In this case, it has us just two ACIR opcodes, and you're probably asking what is ACIR. ACIR stands for Abstract Circuit Intermediate Representation, and it's the way that Noir communicates with the different backends. So I was kind of stretching the truth when I said that it would work with every backend. It would, as long as it can understand ACIR. So you may have a translation process there, which is not big. If you see ACIR, it's pretty easy structure. So you want to care about the circuit size, which is 18, which is almost nothing. Okay, 18. Obviously, I mean, all it does is just proving that something is different from the other one. So it's pretty simple. But this is important if you are tracking how many gates you have in a. So for I don't know ZK Passport, for example, they use like I don't know 600,000 gates, something like that. So yeah, there's definitely I would say a scale that you want to take into account on how many gates you have, because they would hit the RAM limit on the phone or on the browser, especially on the browser in the phone. This is even worse, especially if it's Apple. Yeah, because yeah, the gates are like if you see if you can imagine of a zero knowledge circuit as a hardware circuit, the gates would be the different components. So it could be multiplications, additions. It's all multiplications and additions basically. So the number of gates is the number of you can think of kind of operations that need to be done in order to solve the circuit, in order to prove the circuit in this case. Yeah. So they are not opcodes. I think opcodes here would be I don't know. Just an equal whatever. But they translate to this, and this is what you care about. If you use a different backend, this is not the same. You can't really translate gates from one backend to the other one. for example, 18 gates in a Groth16 backend would be even less than it means for Noir. Like it's just a different way of measuring things. So yeah, you care about gates mostly. How big is your circuit? If you want to prove this, which is what you probably care about. Oh, I already have this because I was doing this project before, but this is in the cheat sheet actually. Going to the cheat sheet, you can see here the things, the command that you can run. So I'm actually gonna copy and paste it and then explain what it does. So Berg prove the bytecode at this location. The witness is at this location. The output is this location. And then the format of your output. This is just so it's easier for later on for us to plug this into Remix. So it will split into two kinds of files. One is a binary, and the other one is just a number of finite fields elements. So that's why I pass output format bytes and fields, and then the Oracle hash. You generally don't necessarily need this one, Oracle hash, if you don't want to verify this on chain. If you want to verify on chain, you want to use a hash that is better for on-chain operations. And so in the case of EVM, Kachak is an easy. I mean, it's an opcode that's used everywhere, so pretty cheap. So you want to use that. So as an Oracle hash, so use Kachak. But if let's say that you want to prove a program and it's not going on chain, or you're using it for Aztec, for example, you just don't use Kachak. Use Poseidon, which would be the other option, and the default, I think. So this is what this command does, and it will tell you what the scheme is. So ultra-honk is the fastest that we have. Okay. That's it. There's an older one, Ultra Plonk. Some of you may remember that. This is the fastest one. Also the most expensive on chain. 1.2 million gas. It's really expensive. And then you have the public inputs. What I was saying, that things are being input into both fields and binaries, which like binary stuff. So we will have to convert actually this proof into a hexadecimal. So in this case, like you have a proof. If we could see this, it will tell you nothing about the private inputs. But the public inputs, this is the public input. I mean, this would be no problem in revealing actually because it's public. But in this case, like our prover will say that one is different from X, one is different from 2, and all I care is to hide the one, right? The one is the secret. So here, nor in the proof or anywhere else, is I can actually delete prover.toml at this point. This does not matter. All I want to prove, all I want to verify now is that this is correct, that this is valid, without knowing what the private input is. So I can do that with bb verify. This will probably fail. Yeah, bb verify. I need to say where it is. Oh, I need to write the verification key. Yeah, verification key is like each circuit. You can derive one verification key out of the circuit, right? If we are Bob and Alice and we're playing a game, I'm thinking of the number 42, and you're trying to guess my number, and I want to prove to you that your number is wrong, that you didn't guess 42. You said whatever number without saying, yeah, I was thinking 42, you lose. No, it's like you just failed. Okay, that's if that was the case, I would generate the proof on my side, but then you would want to verify using the same program that I used. Otherwise, I could just say whatever, right? So the verification key is there exactly for this. So you can have the certainty that you are proving, you are verifying the same program that was proven. So I can, if I am now Alice, all I've done until now is Bob, and then I've proven that Alice has failed. And now, if I'm Alice, I'm gonna generate the verification key. So I'll go write VK. And as you can see, writing VK doesn't take into account anything beyond the circuit itself. So I can delete the proof. Doesn't matter. All that Alice needs to know is what is the circuit that I'm verifying. This is especially important if you're verifying on-chain, because that's what's going to go on-chain. So, not circuits. It's called, what's it called? Well, workshop. So yeah, here's my verification key. Again, I can't really understand what it is. I could go like cat VK or something like that. Yeah. Anyway, so now that I have verification key, if I'm Alice, I can delete the proof. I won't, because it will be useful later. But I could delete the proof here, and I could say BB verify. And proof verification failed. What? It failed for you? That's a new one. What did I do wrong here? Some check verification. Oh yes, verify. Ultra Kachak honk, because of the Oracle hash. You use the Oracle hash. So if you use view proof and you specify the Oracle hash to not be Kachak, in this case you would write the verification key, and then you would verify, it will verify correctly. And in this case, because we are using the Kachak hash as the Oracle hash, then you also need to verify with verify Ultra Kachak honk, which would be the, I think it's there. Oh, okay, that's bad, but it's there. It's in the documentation. But I know why you spend as much time, because it's not in the getting started. It is in the solidity verifier. So you need to go be proof, and then Oracle. So you did this right with the slash Oracle hash. Check. And then BB verify, then AutoCachak honk. Yeah, you need to use a different one. I think actually that if you go BB verify, you should be able to pass also a scheme article hash, same thing. So you can go verify article hash, Kachak, and where is this? Yeah, I mean, yeah, I don't know. Maybe it's not using the correct scheme. Maybe scheme ultra. Okay. Well, I don't know, but yeah, definitely just BB ultra Kachak honk. This. What am I doing now? Verify. Well, what am I doing? You see the documentation. Read the docs. Yeah, write the VK, which that's one thing I may have missed. And then in this case, well, okay, I could just skip to the solidity verifier. But yeah, maybe write VK, and then I'm doing something very stupid, because I just did this just before now, and Anyway, just yeah, I'll try to see if this is a problem in the documentation. You said that it's probably a problem in documentation. Okay. That's probably it. Probably. So I can go say Noir up. So Noir up. This is will this you want to say BB up for this is installing 84. You say 86. Oh, the beta version. Maybe beta 4. The version will always track this one, so I can now do it. So Nargo executes, then bb proof. I think this is it. And then bb write vk, and then bb verify scheme ultra honk ultra check. No, yeah, there's something that I'm missing here. Maybe the K, but I'm also sure that's not gonna be this. Okay. Yeah, there's something really stupid here. Anyway, let's hope that that the on-chain verification works. So yeah, say that. Imagine this worked, and now you wanna do this. How can I do this on chain, right? How can I? If you're playing like a battleships game, you probably want some on-chain. I mean, you could use some kind of um, channel communication that would work. But most of the time, you would want this to go on chain, so you can verify things without revealing what they are. Is means that you could shield funds, for example, revealing all the information about you. You could, I mean, there's just you could vote without revealing your own information. Yeah, there's a ton of things that would involve proving to an immutable ledger that something is true without saying what it is. And my opinion is that it's completely useless if you can do that. So let's just hope that right solidity verifier works. Solidity verifier. So when you write the solidity verifier, all it does is the same thing as the verification key. It just puts it in a smart contract, right? So it's incredibly. It's basically the same thing, and I'll show you. If you see the smart contract, which is doesn't look very nice, but if you can see these all these points down here, I think those are the ones. Yeah, those are just the verification key, right? So this is basically instructions on how to do this without knowing all the information. So you can deploy this, and that's what we're gonna do. I'm gonna go on Remix IDE. Just gonna start a new project. Gonna create a new file. So gonna copy my contract. It'll say, yeah, don't paste. Yeah, I'll totally paste it. Just ignore. And then you can compile it. So it'll hopefully compile it in one go. It will say, oh, it's too big. And I say, cool, yeah, that's fine. I know I'm gonna pay 1.2 million gas. So now I'm gonna choose which one I want to deploy. If you see, all the other contracts are just libraries. So the one you care about is the honk verifier. So I'm gonna deploy this one. You have to optimize it usually. Yeah, yeah. Actually, it may not even work here because of that. But let's see. Hey, it doesn't work. If it doesn't work, no problem. We know it works because there are projects working using this. So yeah, now it's just like doing it locally. All you need is the public inputs and the proof. So we have those already. The problem with the proof is that it comes in a format that it's not easy to copy and paste. So in the cheat sheet, I added a little command that will help you not split the proof. It will just tell you what the proof is. It's a verifier contract. So it will verify your proof without knowing what the private inputs are. The verification key goes into the contract. Yeah. It's hard coded, yeah. So one verification key, one contract for one circuit. No, keys totally it's actually you should be able to derive the key from the circuit. If you have the circuit, you should be able to to determine what the verification key is. And this is very important because if we're playing a guessing game, if we're playing battleships, for example, I don't know where your ships are. You don't know where my ships are, but I make a shot, and you want to prove that I missed, right? So you basically your proof. When I go and verify that proof, I want to know that you are using the same circuit that I'm verifying. So we need to agree on what is the circuit, so we can derive the same verification key, and that's the only way we could play. The problem is that how do we agree on this verification key, right? You could go it like on a side channel and say go on Telegram or Signal and say, oh, here's the verification key, here's the circuit, and then we could play, or you could put that on a smart contract. So that's the biggest unlocker. It's like if when you're using zero knowledge proofs, in this case they are zero knowledge SNARKs, so succinct non-interactive arguments proof of arguments of knowledge. So basically, they are non-interactive. So I can prove to you that I know something without any interaction between us. You just know what I am proving because you can derive the verification key, and then from then on, I just send you a proof, and with only that proof, you can be convinced that I know my private inputs. Yeah, I mean, eventually, it doesn't grow with the size of the proof. So yes, it's expensive. It's 1.2 million gas or something, but it always that. So it doesn't grow. I think it grows with the number of public inputs because that grows with the call data. So, I mean, but that's expected. Sorry. It will always be efficient. I mean, you can. One of the properties is like you can prove a big computation in a very small proof. So it will always be more efficient than pretty much anything. But yes, if you have a lot of public inputs, then definitely, I mean, there are more things to verify against. So that, but they don't grow that much with it's just the call data and a little more. So yeah, but yes, you're right. Like technically, you could have so many public inputs that it will be inefficient. That's for sure. Yes. You can just apply once and use the same one for everything. It does basically because it takes the public inputs. You can use the same for as long as it's the same circuit. You can use it all the time. Yes. Because if you change the circuit, then the verification key would also be different. Because again, the verification key is the only point in contact between who is proving and who is verifying. So Yes. Yes, it would be possible. Yeah, you could definitely reuse the same contract for such a thing. Yes, you could. Yeah, yeah. Actually, that's why some of the parts of the code are libraries, so you could actually deploy them and then reuse them. In this case, we're just deploying everything because it's a workshop. Yeah, we don't we don't work with Ethereum that much on this. Like, yeah, we don't. I would say that this is a side thought because we care about Ethereum because everything on Aztec will be verified on Ethereum, but we care about one contract on Ethereum. That's gonna be very optimized, and and this is something that of course we want Noir to be a nice language for people to use, but uh, yeah, every time I mention that verified contract that costs like 1.2 million gas, everyone in the Noir team is screaming at me and say it's not optimized, and said, did you optimize it? uh, because that's the thing. If we were to put the resources, definitely we could have that much cheaper. Just like it's definitely not our priority. We care about one contract that's gonna be the one that will be verify the Aztec rollup proof. So it's a matter of time. I wouldn't say the priority. I would say time. Just time. Just like in 1 2 years, we're gonna definitely have a much lower uh, gas cost for a Noir proof. Definitely. But one thing that's really cool is like Noir is MIT license. Like it's yours. It's literally everyone's. So you could do it. Yeah. Yes. Yeah. That's an amazing question. Um, See, with when you have a solidity contract, you have kind of the same problem, right? Because you have solidity contract, then you compile it, and then you don't really know that the compiled circuit is the contract that you are actually executing. Yeah, yeah, you can exactly. The same could be done for Noir. That's the easiest solution. Is saying just do the same as Ethereum does. You have a grain check, some kind of uh, Etherscan or something that recompiles the Noir circuit and says, yeah, this bytecode corresponds to this contract. Or you could actually give the contract to be compiled on the client side. And so I think the client side is the mega, ultra mega giga power of zero knowledge proofs. Because if you do it client side, you can give the circuit to the client and the client will compile it. Now you ask, yeah, the user still doesn't know how to read Rust or Noir. That's true, but does it have all the information on their side? They do, right? You can have an AI explain it, which you couldn't if you serve the compiled circuit. There's always going to be a point where they're like the user doesn't know, but the answer will always be give everything to be done on the client side, the proving, verification, everything done on the client side. Yeah, it's very powerful. Cool. Any other questions? Feel free to interrupt. We have time. Yeah. Mm-hmm. Good question. Um, there is no overhead in verification, but the proving will be expensive. Like you're proving that another proof is true. Um, So it is expensive to the point where you can't do it on a phone unless you do it on maybe native apps. Maybe an Android or an iPhone would give you enough RAM to do one such proofs. I haven't keeping track of that, so I'll have to try it myself to know. Definitely on the browser, on the laptop, it works. I've done it in 2023 in ProCrypto, and it was fine. I did a Merkle tree with recursive proofs, and it was fine on my laptop. Um, so it definitely used less than 4 gigs of RAM, and it will take on my laptop. I believe it was like 30 seconds. But this was with Ultra Plonk, so the previous generation with Ultra Honk is gonna be much faster. So yeah, it's there is an overhead. It's annoying enough to not work in a user's phone on a tab on a browser tab, especially if it's an iPhone, because iPhones like Safari will only give you, I think, 300 megs of RAM to use. Otherwise, they'll kill your tab. You know, I used to say that Safari only gives you the RAM you need to open Apple.com. That's the only thing you need to do with Safari is buy more Safari, more Apple products. So that's the only thing they give you. But if you go native with a native app, then you can use more. So that's what ZK Passport use, for example. So yeah, there is no definite solution. Depends on what you want to do. If it's a browser app, with most laptops, computers will work client side. On phones, maybe no. But verification always going to be the huge amount of 1.2 billion gas. Yeah. Yes. Yes. You as a Bob, you are proving that your opponent is wrong, right? So indeed, you could change and say, yeah, the opponent said 42, so now my private my number is now is not 42, it's 43. So they're always wrong. Yeah, you could definitely. So usually on kind of on a game like this, you would commit to this value as you just said, but then you are like, if I commit this value, I need to encrypt it and put it on chain encrypted, which becomes even more expensive. And if you go down that line, I'll assure you that you'll reach to Aztec very easily. Very easily, you're like, oh, cool, Aztec will do this for me. And then you start coding on Aztec. So that's why we built Aztec. It's because Noir is good, but then you're like, if you want to have private state, then Aztec is just a superpower. Yes. And private state on Ethereum it's okay, but I mean, it will always reveal that, like message sender, for example. There are a ton of things that you still don't get the privacy unless you use like relay networks or very complex or complex structures that you need to do. So some people are like, can you do everything that Aztec does on Ethereum? And the answer is probably yes. You probably could with just Noir and Ethereum. You could do everything that Aztec does. It will just be very expensive, very complicated, and very slow. So yeah, Aztec will just abstract away by using just a different execution environment that is optimized for zero knowledge. So yeah, yes, yeah. The circuit is in ACIR format. It's an intermediate representation, uh, and then you use a backend, which could be Berg, to feed that witness, so the solution of your circuit, and provide a proof. And then you could verify this proof off chain by generating a verification key. Give the verification key or give the circuit to your opponent. The opponent will derive the same verification key and then be able to prove that your proof is correct, is valid without knowing your private input, or you could just put that in a smart contract and have it done for everyone. Yeah, it will grow on you. Yes. Yeah. Yeah. So in the cheat sheet, you have this little command. This will basically translate that binary format into an hexadecimal. So I'm gonna do that. So you can go. Yes, we should. It was worse actually before, because before this, before some months ago, the proof would come with the public inputs. Not even at the beginning. You would have to split them, but it would like take the first part and split it and stitch it back together. And I was like screaming at the cryptography team and say, please, please accept them separately. And they'd say, no. So what they did was like they made this proof as filled thing that will output them separately. But yeah, so yeah, this is the proof. As you can see, it's not big, right? Right? It's not big. This is like, if you think that this is the size of the proof of whatever circuit you want, it actually grows a little bit. Yeah, you get out of gas. Maybe you need to optimize the circuit. Yeah, yeah. So yeah, if you can imagine like the amount of computation that you can do in such small proof, this is small, right? So going back into remix, I can actually go and say 0x. I need to put 0x before. I'm just gonna paste the proof, and then I'm gonna paste the public inputs, and that's why I put it. I put the output as proof and field, so I can um, bytes and field, so I can just copy this. Just copy the public input. Again, this is the magic, because you could use a different circuit, a different proof with a different public input. Actually, in most cases, you would want the public input to not be in call data. Like you would want it to be within the circuit. For example, for a Merkle tree proof, the root is in the contract. Like you don't need to feed it. It wouldn't be trusted. So as you said, this is probably gonna fail with out of gas. Yeah. I guess maybe just optimizing the contract here. Yeah, it should work. Yeah. So I just put like 2,000 rounds of 2,000 is a bit too much. Yeah. Yeah. So I need to redeploy it. Just gonna copy the proof so I can use it. Yeah, this is notably hard to get the first time, so I won't blame it. Yeah, same thing. Anyway, maybe I will need some kind of custom gas or whatever. But yeah, yeah, add a zero. Yeah, let me see. That's a good one. No, yeah, maybe. Yeah, I don't know. I don't know. I'll just pretend it worked. Yes. Oh, the right VK also takes the hash. Oh, then that's it. Like right VK. You mean Oracle hash? Get jack, and then right code. Uh, Yeah, that was it. Sorry, I don't know your name. Um, here. So Savio just mentioned the reason why it wasn't working. It was that I was forgetting also to pass write VK to pass also the Oracle hash. So that was the default is Poseidon. So if you do everything in Poseidon, it's nice if you're verifying a proof in Aztec or off chain because it's faster for ZK. But yeah, Poseidon is not very fast on Ethereum for now because I think they are improving. Yes, on EIP. So that would be amazing. But yeah, that was why it wasn't working. Actually, now it could be that I would write Solidity verifier. Maybe now because it's a different verification key. Maybe now it works. I'm gonna compile it again. By here. Yeah, inputs. Cool. Yeah, it worked. Woo, woo. Yeah, that was it. I was forgetting the Oracle hash. This is tricky. I take it. Yeah, exactly. You need to recompile. So the gas cost for this is actually very very high. Let me just see. Um, gas. I can trade for 4 million. No, I can't be wrong. Yeah, yeah. Maybe I can actually try it without it. I mean, if let's see. Since we're trying things. Let me see. Yeah, 2 million. Yeah, just looking at 2 million. It's more still more than I thought. So yeah, I'm probably do some. it that's the thing. It's always going to be too much. Like it's always going to be a crazy amount of gas. So even if it's 200K, it's always going to be too much. So pretty much, yeah. So that's. But again, I'm not denying that there is a trade-off. Like if gas cost is an issue, then definitely don't use Berg. Use a different backend. Use Grout 16. Use I mean, yeah, and that's actually the reason why World ID are using Grout 16 backend because they want to prove multiple iris proofs in one. So they are using their own recursion and their own Grout 16. So it's very cheap to do both client side and then verification on chain. Yes. It's that for Grout 16, if you change the circuit, you can't just use the same. You can just derive the verification key. You actually need to run a trusted setup for that specific circuit. So you need to run a trusted setup. It's a very annoying thing that you have to make like a ceremony, and that's pretty annoying. I've done it once, and it's yes. So can you imagine doing that for every circuit? I mean, it's fine if it's one circuit that you run once and you're like, I'm sure this will never change. It's some simple circuit or it's battle test or something. That's fine. But if you want different circuits, you probably just want one trusted setup, which is the first one when in this case we're using the ignition trusted setup that we did in 2017 or something, and that's it. Like it's yes. Yes, but we did it. You can be sure that we did it correctly because they I think they smashed the laptop or something, right? They did the randomness, and then they submitted that, and then they destroyed the laptop. So yeah, you can be sure that that is a real trusted setup. Yeah, people do the crazy things with trusted setups. They go and measure like radioactivity levels in certain places and stuff like that. It's like, yeah, truly random or almost random, and use that, and then yeah, it's crazy stuff. Cool. And now you're asking me like, this is nice. How can I build an app with this, right? This is where probably I don't know when I should stop. Uh, yeah, in 5 minutes, right? So, but if you're like, oh, cool, now I want to. This is all good in a CLI. How can I do this in a browser, right? And my goal today would actually be to use some AI to build all the front end and then just plug in Noir on top. And but and there's basically a tutorial on doing exactly that, like building a web app with Noir and Berthmer. In my experiments just before coming in, this is exactly what I did. So um, I went like I think V1. So basically, I used the JS packages, BBJS and Node.js, to do this exact same thing, but in JavaScript. And because it can do it in JavaScript, then you can run this. And I can run this, say, temp V1, and I can go yarn or node index.js. This will, yeah, just return true. You could do this in a like in a front end or something. So I could actually just go here and ask ChatGPT or Cursor and say, yeah, you see this? Just make a front end that does this. And it would do it would work. Okay. And then yeah, I mean, yeah, it could take more than 5 minutes for it to build. But you see what I mean? At the point where you have something that works in JS and works on the browser side, then all bets are off. Like you can go and all the Web 2 process can be, you don't need to understand any JS or HTML or CSS. You can just ask all the bulk of the work to be done by an AI. And this is all you actually care about. This is, even AI will still figure this thing out, but if it doesn't, this is all you need to know. So you need to import two packages and the circuit that you have just compiled. You can actually compile it client side as well, which is, I didn't do it here. I don't know why. You instantiate the Noir, the front end. You instantiate the backend, which will be ultra honk backend. This is the minimum age because yeah, this circuit is just an age circuit, like proving that you are over, this case that you are over minimum age. So the prover will be like 22 is bigger than 18, but I don't reveal that I am 22 because I am, right? I'm 22. And then, yeah, the JS thing will do just the same thing. Just execute, then generate the proof, and then verify the proof. And here is where you can actually go use VM and, I mean, generate the solid verifier with like, you go backend, generate Solidity. You basically have all the same Solidity verifier. You actually have all the same commands here. You'll generate the Solidity verifier. You could use VM to deploy it and call using VM whack me whatever you want to do. It's pretty cool. And so this is what the documentation tutorial does here. So you can follow it. Yes. More than being in a browser, it's a static website. Like it just runs. So just to give you an example, it will eat a ton of browser memory, but it's not that bad. It depends on what exactly. That depends on if it's recursive proof, it will eat quite some RAM. but it's not line. So just to give you an example of things running fully client side, this is a demo I wrote, Stealth Drop. So if you don't know Stealth Drop, it's a very old project from Xerox Park that will allow you to claim an airdrop without revealing that you are eligible for that airdrop. So you'd use a stealth address to claim an airdrop. So I did this little demo. It needs to use a plume nullifier, which is a type of nullifier that's different from just the hash of a signature. Yeah, for reasons you can read in the CRC, it will tell you why. So this is run fully like client side. Like there is no backend for this. You can open here the sources, the network, and see that all the things that will happen here are calls on chain. Like so I'm saying because no wallet supports Plume signatures. I'm actually doing this, not mocking it. It's actually signing, but I mean just with a hard coded private key. So I'm signing here. This is just downloading the libraries, the SecP libraries. So again, no backend being used here, and then I'm claiming, and you see this is downloading the WASMs for Noir, the ACVM abstract circuit virtual machine that will interpret the ACIR, and the ABI WASM, the compiler, to understand what the ABI does. And this is executing. It will prove and run. And yeah, so with this, you could claim an airdrop that you are eligible to without using that very same address. You could use a different one. Yes, it should be possible, yeah. Because you would just have to do that. You just would have to do it within a circuit. So if it's if it's like arbitrary computation, um, yes. So yeah, here's like I don't have Cipollio here enough to pay for this, but you whole sky is so yeah, but you get the idea. Here there is no backend for this app, and this is pretty powerful. Like you can't. To me, it's still mind blowing that you could do something like this. Another example would be um, yeah. I can use the memory tab just to give you an idea. Just gonna do the first part here. Um, and here. I can't really read this. I don't know. I can't really interpret these values. But yeah, it's this is enough to run on. So I tried it in her Android phone and it works. So, but does it work on my iPhone, like on a browser? So that's an example of something that is it's cheap enough to work on a phone, but it's not cheap enough for Apple to not try to kill you. Um, oh yeah, I have no idea how to I don't know what I'm looking at. But yeah, I hope you do. Not to go back. No, it's No, no. You would have to know exactly, use some kind of like sourceify thing where you would have a third party that would recompile the same circuit, and basically you would have like some kind of green check saying, yeah, this bytecode corresponds to this contract. Or you could serve the contract to the client, and the client would compile it client side, because you can compile it client side as well. I don't think so. Like, looking at the contract, it's just like it looks like any other contract. Yeah, they like the translation between the verification key and the verification contract is it's surprising. If you go into the Bratenberg source code, you can barely find it. It's a template. It's literally a template, like a Solidity template, and it just plugs the values in there. So it's crazy. Like, the Solidity verifier is the verification key. It just has instructions on how to use it. Yeah. Yes. Everything else is reused. Yeah. Cool. Yeah. They with ultra honk they grow. So they are not constant. They are like a big circuit will generate a bigger proof. Yeah. The verification is always small. It doesn't grow in size. I think it's always the same size. The verification key doesn't take into account the public inputs, because like it's tied only to the circuit. So if it's a big circuit, you have one verification key that's exactly the same size as one small circuit. That's why the actual like gas cost of verifying one proof doesn't change. So if you have like a recursive proof and you want the verification key for that recursive proof, that's always going to be the same size as a circuit like we just did. So yes, but I mean, you could do it smaller ones, especially if you have two. Like, you have two proofs and you want to prove two proofs in one, and that's pretty powerful, because you could, like, for example, for voting systems, if we were in an election, for example, we could vote here, and then we could prove the validity of the votes here in this ballot, and then basically use this proof and verify within like a regional level, uh, verify this proof within another proof that then would go at the national level, and so on and so forth. So you could actually have an election that is all based in zero in a recursive proofs. Like, you have two regions, verified two proofs in one proof, and then so on and so forth until you get to one proof. That's how Aztec works, actually. Like, you when you make a transaction, all that comes out of your phone or whatever, it's one proof that it's already recursive. It's already folded. It's not recursive. It's another thing, but it's already like a, you can think of it as a proof of a proof. And when you send it to the node will do that as well. Like, it will just to the prover will do that. It'll just like go and recurse and say, this is two proofs of one proof in one proof, and then so on and so forth until they get to one proof, and that's the one that's going on chain. That's how you can verify, I don't know, hopefully 100 like transactions per second in 1.2 million gas or whatever it is. So bit asking the limits of my knowledge on this. Yeah. So recursion is like, you just aggregate points, elliptic curve points, and then at the end you just prove that. Yeah, basically you prove the pairing of all these points, So you kind of add them, and with folding, not really. Folding, you provide all of them. So yeah, that is as much as I know. They definitely serve like different purposes. And a funny story is that one of person that was very involved in folding was Ariel Gavzan, and he was working with Aztec. Then he became very interested in folding, and so he started his own thing to research on that. So he left, uh, and because he was like, yeah, this is useless for Aztec because you can't fold different circuits. Always have to fold the same circuit. And then they, I think they went like to grab a coffee, Ariel and Zach, and Zach was proving to Ariel that actually you could use it with different proofs. So it was like explaining to the guy that invented the thing that the thing was actually more powerful than he thought it would, and that's how Ariel came back to Aztec and started working on client IVC. So yeah, that's a funny little story about just having fresh eyes on things. Like even if you know, even if you invent something, if someone else comes with different eyes, different pair of eyes, they will see things that you don't know. So